right, good morning. How you guys doing? The HPLC work yesterday? After all that? Good. All right. Had a brief moment where I needed to update my password here. Gave us some trouble in the lab yesterday. So just every time LSU's like, hey, change your password, and everything will be great, I promise. And then you got to log into 200 different places. Okay, so we left off yesterday, or last time, with a spreadsheet, and I said, well, let me take some time to build it myself and then show you it in that way. And truly the kind of instructions, so to speak, here provide a very nice, convenient way to build it. So you'd be able to build it yourself, and then it could look just like this and have no problem. But then how do you use it? That's probably where I can help you out a little bit. So we're going to talk about this. There's another example. It's very similar. I've got two spreadsheets. They're almost the same. So I'll show you those. And then most of what we'll discuss today, it's kind of starts from here, and then eventually we'll get to deriving the alpha fractions that kind of you need for your assignment on Thursday. As well as part of what you need probably for your homework that I extended till Thursday next week. I still don't think I'll get to the titrations exactly this week. Things are moving faster and slower and different paces than I kind of expect, and using two different books that way, it's a bit of a mix. But I think we're on a good pace. So you just continue to let me know if you're like, I have no clue what I'm doing here or whatever. So at any rate, I think that should be hopefully good. So I'm going to pull up this Excel sheet to share that with you. How many of you have used Excel Solver tool before? Okay, so it's not foreign to everybody. Here's the spreadsheet that I made on my end, and what you can see is they have a table, like a list of the formulas here. You don't need to add those yourself because what it's saying is that's the formula that's in here, right? 10 to the minus B23. That should be pretty much the same formula that we see right here. I just happen to have, instead of B18, I just had a few more spaces, so it's down a little bit, right? But that's calling right here. So this is taking the H plus concentration that the solver is going to guess. So the way this is going to work is the Excel solver is going to say, I'm going to select a number there and change that number until I get the number here to be as low as we can. So this is the spot where we're trying to minimize. Do that a little better. So we're going to tell Excel to minimize that number in this cell. And we've also amplified it so that the small differences will appear larger. And so it kind of gives us a little more space to say, how close to zero are we? By making that really, really tiny number bigger, it accentuates that. So it kind of gives us a little more precision. So that's one of the assumptions we made last time, that, well, we might need to amplify that. Okay, then instead we could change pH as in H plus directly, but like I said last time, working with pH puts us in the log form and gives us, if we check every 0.01 pH value, that's kind of a more convenient range across 14 orders of magnitude than trying to decide how much of a change in OH and H plus across 10 orders of magnitude and do those accordingly. So it's just nice to work with it in a log form, which is why we do that part. Okay, so coming back to the Excel sheet then. To use Solver, you have to first add it in, very likely as an add-in. So if you go to your data if you go into the tab called Data, you will need Solver, which actually my Excel sheet might not even have it on my laptop. Okay, so I guess it's here, but if it was not here, I believe you go to your options, add-ins, and you can essentially select this solver add-in, and then I think you would hit go or hit add or whatever it is, and then it'll say, okay, we're just going to install this into your Excel. Might have to download it. I'm not sure. It might already be preloaded onto your computer and it's just not put into the application because it's not default. And there you have it. So you can Google that if you have trouble. It's relatively straightforward. You just have to follow a couple directions, options, add-ins, add solver. Okay, once it's there, it should give you an option here, and typically it'll even be labeled solver. I guess my Excel here is shortcutting that a little bit. When you do that, when you are ready, essentially what you're going to do is you're going to select the solver. You're going to set an objective. That's going to be the thing that you are trying to achieve. So we're trying to achieve 0 for that solution for H plus that we derived. So if you recall from last lecture, what we did was we said, let's find what concentration of H plus is there in solution, what's the pH, if we have some amount of an acid. So that's our question. We derived some equation based on an electroneutrality equation, based on a mass balance equation, and the other components, the equilibrium constants, we got a system of equations so that we could solve for H plus. That's what we did last time. And with that, then we ultimately came to a left-hand side of the equation minus the right-hand side of the equation equals 0. That gives us a way to find the root or minimize or ask solver to find us the solution that takes us closest to when the right side of that equation is 0, because that's our solution. So that was all kind of the background here. And what we're doing now is going to say, all right, we want D18, which is this equation, the left-hand side minus the right-hand side equals 0. We want that to come as close as we can to a value of 0. Now, solver gives the option to say, okay, I want to maximize that or minimize that, but we don't want a super negative equation, right? We actually want that to be just 0, as close as we can. We already put that amplification factor of 1,000,000. So at this point, that's going to tell Excel, all right, that's the bin, that's the cell that we want to be as close as we can to 0. And how to do it, that's where you say you may change these cells. Now, in some cases, you might have multiple variables. So you could use this system to solve for multiple variables in your equation. So it can do more complicated things, and then it's going to be doing a suite of experimenting, trying different variables, iterating through the process to try to get close to 0 or close to whatever number you set. In our case, we're just varying the pH. Okay, so then we put, for this, we target that cell, right? So that would be B23 in this case. Okay, that's about it. So at that point, we will just hit solve. And it came up with some results and popped them over here. And it's asking me if I want to keep the solver solution or restore the original values. I'll go ahead and keep them. And we can see, so it's still 4.57-ish. Now, one thing we'll see is if I change this, and then we'll try it again, and I just have the image there. It's the same thing. If I change this to 14, we can say, all right, well, that changed the number quite a bit to a negative 1.0. So the difference here is a negative 1 million. We're very far from 0. If I try pH 0, we'll see this is positive 1 million. Okay, so we can already tell something funny's happening if we're trying the extremes. One thing we could do experimentally, let's say we were doing this by hand and without the solver, what we might want to do is start on the extremes, check, let's say, at pH 7 as well. So here we have a negative number, negative 99, I suppose. And so if we think about it, we started at pH 14, we're negative. Start at 0, we're positive. Try in the middle, we're still negative, so the solution is probably below 7. So now we've kind of cut it in half. Let's try 3.5. Okay, now we're positive. Less so than when we were at 0, which was like 1 million, right? So now we're at 313. So it's probably above that number is where the true 0 is. So we could actually go through and just half it every time. And that might be a smart way to do it if we had to do it by hand. Okay, and we didn't know anything else. So let's say that should be somewhere like, let's see, what is 7 minus 3. So 3.5 divided by 2 plus 3.5. 5.25. So let's try 5.25 as our next guess. And we see that's negative. So that's telling us, okay, we're going to go back down, and somewhere between 5.25 and 3.5 would be the next guess, which is getting pretty close to our 4.7. So if we were then to try 4.5, now we're getting to the point where we're 7 above 0. So you can see how this is like really honing down even without the solver. So if we start with an initial guess of 10 and then do the solver, it's going to do all of that for us. We just solve it again. And when we keep it, it's going to say right back down to 4.57. Okay? And if we go above that, we expect that it's going to start becoming a negative number. And if we go below that, it's more positive. Okay, and we see here that this number is not precisely 0. We still have a number there. But if we look at the exponent, it's times 10 to the minus 5. So it's a very, it's close to 0, right? And that's sufficient. So it's not a precise solution, but it's quite effective for that. Does that make sense? Okay, feel like you could do that? Probably a good idea to go through and build this exercise or the next and do that for yourself. Okay. All right, so this is just the same stuff. I just put it here as another reference there. Okay, so another way we can solve these equations, instead of just doing straight solver with a root setup like that, left hand minus right side, right hand equals 0, we can actually take a polynomial approach. But as the book says, well, this is instructional purposes only, to think about how we could do it if we didn't have access to a solver, and why this is not a great way to do it. And that is to take a polynomial. So last time we took that mass balance and we could say, all right, here's the deal. But there are solutions to polynomials like a cubic equation, like a quadratic equation, things like that. And so for this cubic one, if we were to plot this as a function of h plus, it can technically do the same thing in terms of find where that equation is 0 and give us a solution, finding that 4.57. However, if we look at doing this in terms of a trial and error, or like a by hand sort of a thing, one thing we'll notice is it's not a very good shape for doing the root solving. And that's because if you are somewhere below the pH, let's say a prime here, it is going to move you in the right direction. but it's moving quite rapidly. So it's going to be a little bit hard to find, like it'd be much nicer if it was a gentler slope, because a smaller change in pH is associated with, oh, okay, I'm getting closer but not quite there. Whereas with a huge change, it's like instantly you're like orders of magnitude different. Be a little difficult there. So that part's difficult. The other part is if we go to the right, if we go upwards on pH above that, at first we're dropping, which might be helpful, although it's still quite fast. But then we come back up close to 0 again. So if you're just making guesses, we can't do what I was just doing in terms of checking the extremes, right? Because this equation is going to bring us right back up close to 0 again for these high pH ranges. And so that could get really confusing if we didn't have the full plot. So it's just not a great way to do it, and it's possible. It can be done, but it's not great, is the point of all that. Okay, some other better ways to approach finding such solutions would be to make some approximations, which is, something we like to do, especially in engineering. So we're going to go through the acidic solution approximation. We're going to go through an approximation with a weak acid, with a strong acid, and then show that we can kind of do the same for bases. And then we'll move on to talk about how to derive these alpha fractions for larger systems and kind of use these tools. Okay, so the acidic solution approximation, or ASA, it's kind of logical to say, okay, we're analyzing some acidic solution because we've got an acid that we're interested in. Well, it's probably acidic. And so at least for some certain concentrations of the acid, it will be acidic. And then we can make some assumptions. So with that in mind, typically our electroneutrality equation looks like this. H plus is equal to A minus plus OH minus for an acid HA. Well, if OH minus is very small compared to the amount of that conjugate base A minus, which should be true even if we're a little bit acidic, right? So pH 5, for example, that's 2 orders of magnitude away from where H plus is equal to OH minus. So even that will make a very large difference. So if we're pH 3 or 4 or something like that, then this should hold true. OH minus is a lot smaller than H plus. I mean, even at pH 6, that's 2 orders of magnitude because OH minus is going in the other direction, right? So at pH 5, that's going to be, 4 orders of magnitude different. So that's going to hold true, which means OH minus is also a lot smaller than A minus. So essentially, we can assume this is negligible, right? That's the point. So when we assume that OH minus is small, we say that H plus is effectively equal to A minus. This is why when we take a very general approach to chemistry, sometimes we say, let's take HCl. We're going to add hydrochloric acid to solution. We add 1 molar. We then say, okay, well, we've just added about 1 molar of H plus to solution. That's going to be our acidity, if all else, not thinking too hard about anything else. So in general chemistry, in simplified terms, we do that. And here's why we can get away with that, is because it tends to hold true for a condition like that. Okay, so then if we make this assumption, then normally we have to account for the OH minus with a Kw divided by H plus term when we are building our mass balance or our overall solution term. So normally we would have H plus equals A minus plus, and here we would put Kw divided by H plus as a substitution in there. But since that's going to go to 0, we're no longer including it. That's going to simplify our overall term, and we have fewer H pluses there, meaning we're not going to have such a a difficult or complicated route to solve. So then our equation, instead of what we were kind of looking at previously in the last lecture, instead of the more complicated version, now we're going to have this. So, or excuse me, we're going to take, we're going to end up with h plus minus ka divided by h plus plus ka. This here is the term for a minus. We substituted it in there. The AT, that's the total amount of acid, and we have some portion of it that is the total. So this is like saying, this is saying that alpha 0 times AT. Should be A alpha 1, sorry. Okay, so this is just the expanded version of that. Now, there's another thing we can simplify here, because we know for an acidic condition, the Ka, given that we're assuming that we're at least a little bit acidic, then the Ka is also, I'm sorry, that's the next one. That's not this one. So pardon me there. Anyway, this would become the solution then. If we multiply everything by H plus, this will become H plus squared, and we can get the other terms simplified as well. Okay. With that, we can solve with a quadratic equation, which is relatively convenient. We've learned that some time ago. All right, and it was a little ahead of myself with the Ka assumptions, but we'll come back to that. So when can we use that assumption? Well, the book says if we want to be really nerdy about it, then we can get into that. And basically the definition is anytime OH minus is less than 10% of H plus. It holds true enough and works pretty well. So that's actually a fair amount of pH ranges, and it gives a little more explanation about that and some other thoughts. Essentially, when our equilibrium constant times C minus, let's see, that 10 to the minus 6.5, I think that's kind of indicating that's the threshold where H plus is 10 times OH minus. Okay, so anyway, if you care to read more about that, you feel free to, but mostly it's under acidic conditions. Okay, so that was an approximation for when we have just one simple acid, HA. Well, what happens if we have a weak acid, meaning it's not going to fully dissociate? What can we assume then? So here is the acidic solution approximation plus a weak acid approximation. And the weak acid, so we're still going to assume it's acidic, right? So we still have the H plus is essentially A minus. But here we're also going to say that we're not fully dissociating, so, and in fact, a weak acid is mostly not dissociating. So here we're going to say that HA is approximately all of the concentration of our acid. So A total or C is either way you want to write it. And in this case, we're going to do the same simplification as before and get to this point because we got rid of the that OH minus term. However, now we can also say that Ka should be a lot smaller than our current H plus concentration. That's because a weak acid, by definition, does not dissociate all the way. So when we add a lot of acid and we're in an acidic condition, then we have this condition holds true by that definition. So that means that if Ka is much, much more important than H plus, and we look, or much smaller, much less important, and H plus is really the dominant thing. So let's say it's 1,000 times different, okay? if we had on the bottom here 1,000 plus 1, how much of a difference does that make if we remove that 1? Not much to our overall calculation, right? That's going to be a decimal place pretty far out there. So in this condition, we can, at least on this denominator, take that to basically 0 and say, all right, we're gonna kill that term and say, now we'll simplify to say now our equation is h plus minus ka over h plus times the at. With that, we can solve the equation, put it in terms of h plus. We'd have to multiply h plus by both sides, or by everything, and then put the ka times at on the other side. That gives us our square root here. Okay, make sense? So here now we have given 2 approximation assumptions. Now we get a first order equation that's quite simple. Okay, what about a strong acid? We can do the same type of thinking. We're also going to assume we have enough acid to make it quite acidic, or at least acidic enough. And then a strong acid means we're pretty much going to be completely dissociating. So no matter where we're at, our total amount of A minus is going to be approximately the total amount of acid. So this would be much like adding HCl to a solution, and we know that since the pKa for that is negative, it's all going to dissociate. And at that point, we have H plus and Cl minus. So if Cl minus is the A minus here, then what we're saying is the total amount of Cl minus is basically the total amount of acid that we added, right? So that's kind of what we're saying. So that's the strong acid assumption there. And then what we can recognize is, well, H plus, we're already kind of solving it. H plus is the amount of acid that we added. We don't have to worry about OH minus in the electroneutrality equation because it's very small, right? So if we took the ENE, what should be H plus on the left and all the minuses on the right, which would be A minus and OH minus, what we've done is we've taken this to assume that's 0 based on the acidic approximation. And there we go. Because we can assume that the total from the mass balance, total H plus is equal to the amount of concentration there, we're kind of done. And here we come back to what I was saying earlier about, in general chemistry, in simple terms, we often will just say, well, if we added some H plus, HCl, that's how much H plus there is, right? Of course, that's assuming there's not too much else going on. Okay, make sense? All right, so these approximations, if we graph them on this strange little graph here, we can see at what ranges of acid concentration are they valid, given some dissociation constant. So given some pKa, so log Ka here on the bottom, if we were to put these as pluses, that we'd just say pKa. So given some Ka value on a log scale, and given some concentration of acid, so this is the acid concentration on the y-axis. That means the higher we go, the more acidic it should be. Of course, it depends a little on what's going on, but in general, that's more acidic. And on the x-axis, this is essentially where the equilibrium point, equivalence point for the acid, where it's going to be crossing between A minus and HA. When those two are equal on the pH scale, that's what this is describing. Okay, so this would tell us if it's a strong acid would be down here, and a weak acid would be higher up. So it's kind of the pH scale sort of there. But then the really where pH is the values on this table. So really what I wanted to show you is under some conditions we can use the acid acidic solution approximation, ASA, with a strong acid as well. That would be in this corner. Anytime we have a acidity constant less than -5, log, less than pKa of less than 5, then it's valid, and a concentration above about 10 to the -6. Now, at some point, we're going to end up needing the we have an intermediate condition where in the green here we have the ASA is valid, but not the strong acid or the weak acid, because we're kind of somewhere too close to in between there. So we can only use the acidic solution approximation. And then for a bunch of it, we can use the weak acid approximation and the acidic acid approximation. Okay, so it's kind of hard to wrap your mind around all of that, but if you do look closely, you'll notice all the pH values given are low. So all of them are 6 or below. And we can kind of just get a sense for if we know something about the acid that we're using, the constant, and how much we have, we can make some approximation. That's kind of the point, is there are ways to make approximations accordingly, and there's a lookup table for it if we wanted to. There's also going to be a lookup table because we can do all of this with bases, just like we've done with acids, and we'll take a quick look at that kind of stuff too. So, speaking of bases, we can do the same thing here, and in this case, we are doing the same thing, except this time the y-axis would be base concentration, and the x-axis is log of the Kb, so the base equilibrium constant. So that is essentially the inverse of log Ka, and we'll talk a little bit about that. And as you see, the pH values that hold true for these are at least 8, just like, or nearly 8. Just like in the inverse case, the pH values were at most about 6. So it's kind of the same approximations, kind of the same range where they're valid. It's essentially analogous to what we just talked about. And it's just making these assumptions. If we're dealing with a large pH, then there's very little H+, right? It's a very small number. So given that, we can make those assumptions within our mass balances and move forward. And by definition, a weak base has a log Kb value of a certain range, and we can make assumptions there as to how much of it is in the HB form versus B minus, or B plus form. Yeah. Okay, so let's take a look at putting that into practice. We'll just walk through this together without stopping, making you solve it yourselves. But we'll see what it would look like to kind of apply one of these approximations. So we have distilled vinegar here, and we can talk about what we can buy from the grocery store. It's often labeled as 5% acidity, and that's meaning that 5%, that the solution is 5% by weight of acetic acid. So that means about 50 grams of acetic acid per kilogram of solution. Okay, and that should be about 1 liter, so we'll go with 50 grams per liter. So the question says, what is the formality? So that's the formula weight or formula concentration. So if we take acetic acid, the molecular weight of acetic acid, and calculate 50 grams of that in 1 liter, how many moles per liter is that? Even if it dissociates, that's the formula weight, right? In the 5% vinegar, so it's a pretty direct molar calculation there. And then B, if the pKa is 4.76, which looks a little familiar. That's pretty close to what we were solving earlier for the previous example, right? In the Excel. If that's the condition at 25 Celsius and 1 ATM, and we can ignore activity coefficients and any minor components like dissolved CO2, what is the pH under these conditions? So, excuse me. Solution to part A is fairly simple. We have to add up the molecular weight for acetic acid at 60 grams per mole. Then take that 50 grams per liter, multiply that, and we get, or well, really divide by that molecular weight, and we get 0.833 formula weight, or F, so moles per liter of that original molecule. Okay, so then part B, here's where we need to apply one of these approximations, or to take a look at our Excel sheet, we could also do. So for this solution, the A total, that's what we just solved. That's the total amount of acid is 0.833 moles per liter. That's rather concentrated, and this is a fairly weak acid, meaning that's good conditions to apply both the acidic solution approximation and the weak acid approximation. And what we'll notice here is even though it's a weak acid, if we add a lot of it, we're dropping the pH quite a bit, right? That it does not mean we are limited to an acidity of 4.76 pH. Okay, so given that, we could look back up and see what was our condition for weak acid and ASA. Well, or we could derive this ourselves again by saying, okay, let's get the electroneutrality equation and set it up and solve for it and go through these steps, but we'll see that we can say that the total acidic concentration, that should be mostly HA in that form. And so that gives us the approximation here, and we get rid of the Ka down there. What we're left with is H plus should be equal to the square root of Ka times the total concentration. And we know this, and we're given this, right? So that means we can solve just by taking the square root of the product of those two. So when we do that, H plus should be equal to 0.0038, and we take 10 to the minus log of that, and we get 2.42, or minus, yeah. Okay, so 2.42, now that's it's quite low. So if we were to drink straight up vinegar, well, of course our stomach has a probably lower pH because it's making a lot of HCl, but maybe you'd have some concern for how your teeth are doing with that condition, right? The dissolution reactions there. And I think, I haven't checked this, but I think if we go back to our Excel sheet, which I need to pull up again, this might be the same acid, and we could check that and put in the concentration here. So the Ka 1 times 10 to the minus 5, oops. If we put in Ka as 10 to the minus 4.76, and then we put in a total concentration here of 0.833. And then we tell it to solve. I'm thinking we should probably end up getting the same answer there. Now I could be off on this, but I think this should work. 2.42. There we have it. I'm going to see if it'll let me undo. Ha, it won't. And it already saved. Okay, so I probably ought to switch that back to the original conditions for just a moment. 1e to the minus 5. And this was okay. I think that's all I changed, right? Okay. So very nice. So we can get that answer either way, and works out well. And this is why we can make good use of the approximation, because this is one simple calculator check. Square root of this. What is the answer, right? When you kind of need the solver if you're going to do something without nice approximations. All right. Any questions on that? Okay. I'm not planning to test you rigorously on, okay, when exactly can you use this one or that one? If anything, the concepts of what allows it, maybe where does that mass balance come from? What kinds of assumptions are we going with? Really just understanding we can take different approaches based on what's needed or what's possible. Okay, briefly, we'll mention that we can do the same whole same thing with bases, and it's going to be quite the same. Now, typically we'll use sodium, so NaA, as instead of having the proton there, HA, we have sodium Na. Now we could use potassium, K+, just the same way, because Na or potassium or whatever is really just going to be a spectator ion. It's just there to allow it to show up. But using sodium and assuming activities are still 1, here's what we can do. We've got 5 species that are unknown, just like last time. And that means we need 5 equations to simplify down to just H+, or I guess we could target OH-, but I think we'll probably stick with H+. All right, so we have the water equation, of course. We have our acid equation for the A- that's in solution. We have our mass balance to say the total amount of acid is here, and we can define that, or base. And we have some mass balance on sodium as well, because we know that the only source we added was from adding that NaB. And we have an electroneutrality equation where H+ plus Na+ is equal to A- plus OH-. Okay, so just like last time, we have all of these pieces, and we can go on and essentially derive our answer. Now, on the way, let's take a quick detour to say we can derive a Kb, which corresponds to Ka, and it's kind of the inverse. Okay, and I think I mentioned this earlier, but we didn't go into it. So when we have A- in solution, we could think about it as HCl would be HA, and ACl would be NaA. And so likewise, we can add NaOH, which is kind of the opposite of NaCl. So thinking about that, more specifically, just thinking about the fact that NaCl and HCl are kind of the same deal. We just substitute the proton for something that's not going to do anything. Then some of this A- should react with HA, at least for most conditions where Ka is finite. If it was infinite, maybe we could have 0. But we'll have a little bit of it. So that means HA is present, and in some examples, there might be a lot of it. Okay, so then our system is A minus plus H2O should yield some HA plus OH minus. To get KB, we can then say, flip what's normally we say HA is in equilibrium with H plus and OH minus, H plus and A minus. And if we invert that and swap it, we can say this is Ka to the minus 1. Or we could solve and get the Kb here. And how we can do that is by saying, well, for this equation, which was, like I said, kind of the backwards, so we can say, this is adding these two equations. So that's going to add our A minus plus water gives us HA plus OH minus, and adding the backwards version of our H plus and A minus in equilibrium with HA. So if we add those two equations together, we get this guy. And then we're going to solve for a K and call it KB. So the products over the reactants here, we'd have HA times OH minus divided by A minus. H2O goes to 1 in this type of a equilibrium equation. And this is our KB. So it's a way where we can get the base constant given some Ka value. Again, I don't think we need to deal with this too much, but just to show you that it's here, if we ever did need to do with it, there's a way to handle it. There's a correspondence between Ka and the so-called Kb. So Ka times Kb is going to equal the Kw, and that's going to be something we can note based on this relationship. That also means that the log Ka plus the log Kb is equal to the log Kw because of the log rules, which means the total pKa plus pKb for a given species sums to 14. So it's kind of just saying, just like pH and OH minus, we have some relationship that sums to 14 if we, or some, like the two together multiplied gives us 10 to the minus 14 in water. In the same way, taking the acid constant plus its inverse is going to total to 14 on the log scale. Okay, so that's the deal with these KBs. Given that, we can deal with this these base simplifications. Okay. Otherwise, it's pretty much the same stuff. So when we want to solve for the speciation, that's what we do, just like we did in the acid conditions. The only thing is we're adding that sodium. Okay, so we're going to look at those strong base, simplification, the weak base, all of that in a moment. But first, let's take the analogy of when we're trying to do that left-hand side minus right-hand side, the root solving equation. Again, this is almost the same thing. We already kind of know what we have to do. We're just adding sodium into the solution here. The electroneutrality is the same otherwise. We add the sodium and we go through the same process. We substitute and we end up with an equation here. H plus Na is equal to this fraction that is A minus, alpha 1 times total, plus this amount of OH minus. Set that all equal to 0, left hand minus right hand, and solve for the root. There's a table that kind of highlights the different the differences between using HA and NaA. So on the left-hand side, we have the HA. On the right-hand side, we have the NaA. So table 5.2 might be a nice place to look if you are needing to parse out the differences here, but truly it's the same process. So we took a look, we kind of understood how we derived this partly last time and a little bit more this time. So put that into Excel and use it. It's the same thing, just a tiny update when we have that NA plus. Okay, so take a look there if you are particularly curious. My point is just that we've done it, we understand how to do it. It's this process. We need these systems of equations and setting h plus some function of h plus equal to 0 and minimizing that. Okay, so given that, we can do another Excel sheet, and it looks and works just the same basically. And in this case, when we put in what the book tells us and we want to use a solver this time, the pH is coming out to be 7.4. It's just popping up on my window here. Okay, yeah, 7.41. So there's not a whole lot to say here. I did put bold the differences. So the sodium NaA concentration, we're adding the NaA here. And of course we have this one as well. So there's a few updates to what the equation looks like, but overall it's almost the same. Okay, so just wanted to note that, and that's what we see here. Okay, so back to these approximations to simplify. The BSA, basic solution approximation, is the same logic as ASA, so I'm going to breeze through this so we can get to the alpha fractions of more complicated systems. That's what I want to spend a few more minutes on. We can do the BSA alone, and as we learned from the acidic condition, sometimes that's the only thing we can apply. So here, it's just the inverse, right? We're going to say that H plus goes to approximately 0 is the thing, and so we can then derive an equation where we are solving for OH minus, and if we have nothing else, then we end up with this guy down here. Okay. Let's see. Okay, we did a proton balance equation there. Okay. So we can, I'm going to skip some of these derivations. The book has more to say about it, but we can get it, and it looks a lot like what we had with the ASA, that second order equation there. Okay, same process if we do the BSA and weak base approximation. Here we have some definitions of what a weak base is, meaning that it's mostly going to be in the A minus form and not the OH. Let's see, it would be NaOH form, let's say. Then under these conditions, we can get just the same, this square root condition. And you see here, we can use Kb here instead of dealing with the complexities of using Ka, because it would be a little bit more complex that way. That's why it might be nice to simplify it into Kb. And we can take the strong base approximation where it would still be in the HA condition, and we'll get essentially OH minus is equal to the total concentration of our C. Okay, so I know I went really quickly through that, just saying it's kind of the same thing, just inverted a bit. Okay on that? All right, so let's talk then about the alpha values for diprotic acids. And here's where I think what you need for Thursday, the MATLAB assignment, should come clear. So hopefully you've had a chance to think about it and see, okay, how would I do that? And here's the pieces that I hope will lock it into place and be like, oh, okay, here's how that fits together. So carbonic acid, as we're going to deal with Thursday and later in the class as well, it's one of the most important systems in in most aqueous systems because we have CO2 in the atmosphere and it's going to dissolve into a diprotic acid. The book puts a little star by it and says, oh, we'll deal with this later. I find the book to be a little silly that way without just saying like, we're going to star this. And as an explanation to the asterisk is, we're going to cover that later. Well, why do that? It just means it's going to dissolve as CO2, and CO2 will be then in equilibrium with H2CO3, I think is kind of what the point of it. So we will kind of ignore it for now. We're just going to call it, in this case, H2B, because that carbonate would be the B, and the H2 would be H2, right? So that form here is a diprotic acid. So in this case, if we have some H2CO3 or H2B, then we also are going to have some HB minus and some B2 minus. That's kind of by definition. We're not going to be dealing with HA and A minus this time, because that's a monoprotic system. That's just the way we've labeled that. And so B then is our diprotic acid. All right, so then to solve for the fractions, well, the basic consideration here is the first and foremost the mass balance, right? The total amount of this diprotic acid is the sum of all the parts, right? So we could say B total is H2B plus HB minus plus B2 minus, the concentrations of each of those, right? So given that, the fraction of any of them is the portion of whichever one we're talking about divided by B total, right? That's kind of generically. So then that makes sense that the alpha fraction for H2B is H2B over that stuff, HB minus is HB minus over that stuff, and so on. We can also write these to say them like this, right? So the B total times the alpha zero fraction is H2B. So we have all these definitions. These are coming from the mass balance. This is a starting point, and the challenge is, okay, how do we simplify? Because each of these has 4 unknowns, right? Maybe we know the K, the equilibrium constant perhaps, but how do we put all these pieces together to get a solution to understand the speciation or the H plus concentration given all this mess, right? But here's the starting point. We know the definition of these alpha fractions. Okay, to begin simplifying, we're going to start with alpha 0. That's going to be, just as a reference, we have H2B, which would be like H2CO3, in equilibrium with H plus and HB minus. This is the first deprotonation, and so alpha 0 is giving us the fraction that is H2B. It's relevant to this equation, and the K1, the first dissociation, is going to happen. We're going to have an not equilibrium point, equivalence point between H2B and HB minus at the first pK value. Okay, we'll come back to that later. So we can simplify this first fraction here. This guy, if we divide the top and the bottom by H2B. So that's what we're doing here. And we get 1 over 1 plus HB minus divided by H2B plus B2 minus divided by H2B. So we've just divided the top and the bottom by H2B. From there, we can also recognize that we can simplify really each component. So let's divide, this is 5.74 by 5.73. So let's take a look back. We're going to divide this guy by this guy and see what kind of simplification we can get there. And I think we're going to do that for both this one and this one. Essentially, it's taking the alpha 1 divided by alpha 0. Oh, excuse me. We're going to do alpha 1 divided by alpha 0 and alpha 2 divided by alpha 1. So if we do that, we notice there's some interesting simplifications here. So if we take these and each of these alpha fractions is like the fraction that is in HB minus divided by the fraction that's H2B, or the fraction that's in B2 minus divided by HB minus. All right, so what we can find is those simplify pretty nicely. In this sense, the alpha 1 fraction is the ratio of HB minus to H2B. We could rewrite that as, and by the way, this looks quite obvious once you stop and think about it. When these guys are relating to one another, where they're, let's say when approximately most of the solution is 50-50 between these two, and the B2 minus is pretty small, let's say a low pH, then, well, 50-50 would be 50-50 here, right? Between those two. So it kind of makes some intuitive sense once we start seeing that. But even if we just take these large equations and divide one by the other, what we'll find is it simplifies here, and then we can say alpha 1 is equal to alpha 0 times HB minus divided by H2B. Likewise, with alpha 2 and 1, we could get alpha 2 is equal to alpha 1 times B2 minus divided by HB minus. Okay, so all of that's algebraic. We can also have some intuition there and see that, like I mentioned, but that's all algebraic simplifications working to try to tackle this problem to simplify things. What we need now is to take these and put them in terms of the k's that we have and the h plus. So what you'll notice here, and if you've solved problems like these before, you probably noticed we tried to get them in ratios like this. We want to substitute for these ratios using Ka and H plus. So whenever we have K, it's a function of H plus and ratios of the other species. So KAs. Does that make sense? Anytime we have this equilibrium constant, it's saying products over reactants. Some of those products are H plus, some of them are B, some form of B, right? So if we can rearrange the K equations and then insert them here, we'll be in good business. So that's the next step. Okay, so for H2B in equilibrium with H plus and B minus, that's K1. So K1 we can write as the products of the reactants H plus times HB minus divided by H2B. Well, if we get that in terms of just K and H plus, we have this ratio. And that ratio we can then insert into some of these equations a moment ago. So anytime we find HB minus divided by H2B, right here, for example, here, we can insert that K1 divided by H plus. So that's where we're heading. We're going to insert Ka and H plus values into these equations as we pursue the simplification. We can also insert that right here, right? That's the same group there. Okay, likewise, when we consider the HB minus in equilibrium with H plus and B2 minus, we can get the K equation, and this time we get a relationship of the B2 minus divided by HB minus is K2 divided by H plus. So just the definitions of these equilibrium constants here. So these will be used for substitutions. These relationships here, and that's kind of the target. Finally, we could consider H2B in equilibrium if we combine these equations with 2H plus all the way to B2 minus. So we can get that by multiplying K1 times K2, or getting this net equation together, and that would give us a relationship between B2 minus to H2B directly. Okay, so taking all of these pieces together, we can solve for an alpha fraction for alpha 0 to be 1 divided by 1 plus this guy plus this guy, which is the second part of that. Okay, so that's K1, K2 divided by H plus squared. Now that expansion, we would find the same value if we simply came here and did it stepwise to put both of those equations in to get to this value. But we just did it together first and found that. Okay. We okay on this? Some algebra, lots of substitutions, getting to the point where we can find that alpha fraction. Now we can take the same approach for alpha 1 and 2 and derive it all that way, but it's actually a little simpler if we pause and say, well, we already noticed these ratios that were helpful, and so why don't we just define alpha 1 in relation to alpha 0, right? That's something that we could do, and if we look back, that's something that we were already working on right here. Right, we kind of already mentioned, well, we can get these in relation to one another, so skipping back up ahead, let's do that instead of deriving and solving each one of those pieces there. So we can describe it this way and ultimately get alpha 1 divided by alpha 0 is equal to K1 divided by H plus. So that would say we can get alpha 1 by writing alpha 0, which was the equation we just found here, and multiply that by that K1 divided by H plus. So that would end up putting us at K1 on top, which we could probably divide from the top and the bottom, and an H plus, which we could on the bottom, which we'll multiply across. So likewise, we can do that for A2 in relation to the solution we find for A1. And what you'll find is this is ultimately a recursive process. We are kind of adding that K value and the H value to the system each time we're stepping across and to another alpha fraction. So the book gives a nice table then that kind of pulls all this together, and I've got this on 2 slides here. So we go from the monoprotic system, which we had talked about previously, that looks like this, with an alpha fraction here, 1 over 1 plus Ka over H plus. And then when we go to a diprotic system, we end up with the alpha fraction here with 1 over the same piece plus this guy. That's the new piece. And so if we were going to a triprotic system, what we would expect if we had triprotic would look probably, if we had to guess, right, would be plus K1, K2, K3, divided by h plus cubed. Right? Seems like that would be the logical next step. So we can see we can actually solve a lot of systems in that manner. You know, I don't think we have anything higher than a triprotic system. It'd be a pretty funny type of acid if we did. Maybe there's something weird out there, but that's then what we can do. And we can also find each of the alpha fractions accordingly. Okay, so that's the derivation. That's how we can find each piece there according, each alpha fraction according to the k's and the h pluses. It is also possible to, yeah.
So for the MATLAB assignment, do we have to show all the derivations, or we can just write the formulas down and calculate it?
Let's see. Did I probably asked you to make some notes in it showing your work, right? I want to see that you kind of understand where it's coming from. I don't need you to repeat like every line of text in the book in your MATLAB code, but something to show, you know, perhaps where this alpha fraction is coming from, or maybe the fundamental simplification you did, something like that, would be good. Show me that you understand where it's coming from. Yeah, that would be fine as long as you add enough comments in the code to describe what the code means. In addition to it functioning, you have to be able to communicate what it's doing to someone who doesn't know. That's an important part of coding. Because that person could be you in a year. When you look back on it, you're like, I know I did this one time. You look back and what is this? That's actually a very common thing with computer programming. And so if you do any of it at all, you might as well learn how to do it right in terms of building the habits to communicate with it in addition to causing it to do some function for you. Okay. Okay, we'll just take a quick note here. We can also take the solver root approach to solving for diprotic systems. We've already talked about this a couple times now in terms of, okay, set it up, starting with this electroneutrality equation, include all the mass balance and everything, get an equation for H plus, given the unknowns, and set up left-hand side minus right-hand side equals to 0 and tell solver to solve it, right? So we can do that, and that's quite a possible system as well. We can do it for a system that's H2B, for NaHB, or for Na2B. It all comes to the same equation, really, no matter the case, and we just have to adjust, if anything, the mass balance of the amount of acid we're adding, right? If we add NaHB, that's a little different than adding H2B in terms of how much concentration we've added. However, everything else is the same. So all we have to do is adjust that. In this case, Na2B, Na is equal to twice the concentration of our acid, whereas NaHB is equal to 1 time. Okay. I think that's about it. And we'll get to pH versus C, like concentration diagrams next time, which we've already talked about a little bit, but we'll go in depth on those next time, which is, I think, also kind of part of your MATLAB assignment to plot those. So should be a good opportunity for you to plot it. You're welcome to look ahead in the book or some other books on that. That should be chapter 7, I think, or 6. Yeah. Okay, so see you on Thursday.